Check. Can you hear me, people online? Thank you. All right, welcome back. Hopefully everybody got a nice break. All right, so we'll continue on the second order differential equation. Okay, so just to give you a very quick, brief review at it here. It's been a while, so I'm sure some of these things seem to be a little bit distant. Okay. So this is what we done in the week before the break. So we talked about how to solve a second order differential equation with f of t non-zero, or what we call this non-homogeneous second order differential equation. And we also focus on the coefficients where they are constants. Right? So the first approach that we have done is the so-called method of undetermined coefficients. And we have a different name for it. It's a name is called the lucky guess approach. The name, why it is called the lucky guess, because the method or the approach is based on what f of t looks like. Yes. Sure. Okay, that's the loudest I can get. Yeah. Okay. Okay. Good. Just like the name suggests, we trying to find a solution by making a guess first based on what f of t looks like. So this table here, which I have a handout. I don't know any of you have a handout that I gave out on the last Friday. So if you don't, I do have a few here. Okay. Who doesn't have a handout? I mean, this handout is essentially from our lecture notes. Okay. Oh, actually, sorry, I forgot to mention. Midterm grades is out. You know, I got a lot of email from students asking about to review the midterm, which certainly I can do that with you. Okay, no problem at all. Midterms are marked mainly by TA. So what I would do is I would suggest that you get in touch with the TA first, okay, your TA for your tutorial section, and make appointment. Okay. If there's obvious mistake, so TA can certainly change that. If not, if the TA cannot decide, then we can come back to me, then I can make the changes if necessary, okay? And I posted a solution already on the Canvas, so take a look at first. See if that sort of match your expectation or not. If not, then you can approach the TA, right, or approach me and trying to go through the midterm. The midterm average, to be honest, a little bit surprised, it's not that good, 60%. So it's on par with last year, okay? So we had to say, is it that you don't know what to do, or is it the TA marked too hard? Never know, right? Yeah. So anyway, so we have a process to go through, right? If you really feel that the marking is not fair, you can always come back to me. Okay. Yeah. So let's get back to the lucky guess approach. As the table suggests, right? If your f of t takes a format of exponential function, then your choice for the particular solution will be in this format. Okay. Yeah. So that's your YP. So if you recall that the solution of a general solution for this, right? The general solution is y equal to YH plus YP. So YH is the general solution to the homogeneous equation. So this one we have already done, so we can certainly get the YH based on whatever approach that we have used. I integrate from the previous lecture. So this lecture here is focused on YP, right, or this table here. So your YF of t, if it takes a cosine or sine or combination cosine sine, then your lucky guess for YP will take this format. So that's what this table basically will help you with. And to help you start with a lucky guess for the YP. However, there are a few rules, okay, that you have to stick to. The first rule is a basic rule, which is exactly what we have just iterated. Okay? So you base on the look of f of t to pick a choice for YP. That's the basic rule. Now, modification rule basically means sometimes, mostly particularly associated with this term at here. Okay? Yeah. So if your solution has, if your basis for the YH, okay, sort of a duplicates with your choice for the YP. I'll give you an example next. Okay, then you have to multiply by a t, trying to differentiate, okay, from your basis of the solution. Now, sometimes you do have a repeated root, right? So when you solve for YH, if you recall, the solution of this might have a repeated root. So there is a chance that your choice of YP actually duplicate, twice. So in that case, we have to multiply by t squared. Right? So bottom line is, right, this YP out of here. So YP, it needs to be different from the Y1 and Y2, right, for YH. So YH equal to CY1 plus CY2, if you recall that. So your YP has to be different from the two, what we call this is two basis solution inside the YH, the general solution for the homogeneous second order differential equation. So that's a modification rule. A sum rule, we'll look at an example next, is that if your f of t is a combination of, let's say, exponential and sine or cosine, then you're essentially just, you can treat them separately. Okay, you can add two lucky guess, this one plus this one. Right? That's what some sum rule basically is all about. So that's what we have done in the previous lecture, and we sort of done a few examples for each one of the different rules. Okay, so let's look at a few more examples. Okay, today. So this table, right, is just an illustration of, what you could do based on the f of a t. Okay. So you look at this one; those are simple case, right? The first few is sort of simple case, and then this is a combination of polynomial and exponential. So you have a multiplication of these two lucky guess at here. So that table, those are probably going to be a little more complicated, right, case, but you already would deal with a simpler case like this. All right, so let's look at one more example right here. So let's say I have a non-homogeneous second order differential equation with constant coefficients at here. So this is your step one, is to write down the characteristic equation and then solve for lambda, and you get the lambda is 1. So there's only one solution. It's a repeated, okay, roots, it's double roots. Okay, so lambda 1 is 1, lambda 2 is also 1. Okay. And according to what we learned for homogeneous second order differential equation, then under this situation, the solution is, okay, C1 e to the power of t plus C2 t times e to the power of t. I mean, this is basically as I said, C1 y1 plus C2 y2. So your e to the power of t is y1, t times e to the power of t is y2. Those are y1, y2 are what we call the basis solution. So, okay, so that is the solution for YH. A second step is to find the particular solution YP. So this is the step where you go to this handout, go to the table, okay, using a lucky guess approach. So this function f of t here is e to the power of t. So you go to your table, you look at this table here, that's the first row, right? So your lucky guess based on the first row, based on the basic rule, right? So first, so it's based on basic rule. And we will see initial choice for yp is, it's called, this is a c times e to the power of t. Doesn't matter what letter you use, okay? And the table we use c. Okay, so you can use a, whatever you want for the letter here. It's fine. So this is your initial choice based on the basic rule, right? Not always you, especially if your solution here involve exponential, you don't necessarily stop. You have to go to the modification rule, see if it's necessary to apply the modification rule or not. Okay. So now let's say you look at the modification rule. So what is the modification rule? Modification rule says, look at your choice, initial choice yp, and compare it with your basic solution y1 and y2. Okay. So if you compare, so first you see, if you see et, let's say verse that y1 equal to e to the power t. Okay. So you can compare these two. So these two apparently is exactly the same, right? I mean, this C1, C here is just a constant. So this is the same. Then if they're the same, according to the modification rule, right? You have to make your YP to be different from this. So then you say YP equal to C times T e to the power of T. So this will be the first modification, right? Based on your first examination with Y1. So that's first modification. And then you compare again, you have to keep comparing, okay? So you look at your modified YP and you worse the Y2, okay? So you worse this Y2 here, and you can see, oh, okay, somehow they're still the same, right? Same kind of function. So then according to the modification rule, and what you have to do is you multiply another t. It becomes ct squared e to the power of t. So now this time, the choice for the yp, right, has nothing to do with y1, y2 anymore. Right? They're different by any means. Okay? So then you don't have to do any modification anymore. So your final choice for the yp, right, will be this ct squared e to the power of t. That's what modification rule basically means. And there's also a trick is, now if you forgot to look at the modification rule, okay, and you basically substitute this yp equal to c to the power of t back into the second order differential, try to solve a constant c, chances are there'll be some funny things happen. There's something that you cannot explain. You'll find either c equal to 0 or something. So if that happens, that should be a warning sign to you. There's got to be something wrong. That's not what should happen, right? So that's what I mean by some sort of phenomenon you can observe, right, when you're solving the question. Any question on this modification rule? So as I said, this is a very important rule. It's a trick, it's a pitfall. So chances are you'll be tested in a final exam. So now coming back to this yp, ct squared e to t, this is not the end of it, right? We need to find the value of a c, okay, in order to obtain the general solution for the whole question. So the next step, so you can call step 3, right, to find this c value. And to find the C value, what we do is we calculate YP prime. So this is a product rule, obviously. So you got 2t times c e to the power t, and then plus ct squared e to the power t. And then calculate yp double prime. So there's more product rule here. So 2c e to the power t plus 2tc e to the power t. 2tc e to the power t plus ct squared e to the power t. And correct me if you see any mistakes. Okay. So that's your YP double prime. So far so good. Yeah. I mean, these two is the same, so that's 4t plus c at the top, 4ct e to the power t, ct squared to the power t. Right, so now this is your YP prime and YP double prime, and you also have your YP over here. Then the next step, you substitute YP, YP prime, YP double prime into your original equation, into that Y double prime minus Y prime plus Y equal to e to the power t. Substitute back into the second order differential equation. So this is the where you have to be extra careful. When you substitute back, you're supposed to group all the similar terms together, right? So Y double prime is this, so that substitute into here. Y prime is this, and that should be going over here. And this one should go over here. All right, so let's write it down. I don't have solution in my lecture notes for this one, so might as well just work it out. Okay, that's Y double prime minus 2Y prime. So it's 4ct e to the power t minus 2ct squared e to the power t. And then plus Y prime, which is ct squared e to the power t. Equal to e to the power t. Give you a little bit of time. Also give myself a little bit of time. Okay, so far so good. Okay, let's see what we can do to cancel. This cancel this, right? And this plus this will cancel that. And then you get 2c e to the power t equal to e to the power t. So that's pretty obvious. Your c equal to 1/2. Okay, so then you can summarize. So your overall solution is y equal to yh plus yp, and that's c1 e to the power t, c2 t e to the power t, plus 1/2 t squared e to the power t. So this is the type of solution, right? I mean, the steps are fairly general. First step is always to obtain YH. Second step is to make a lucky guess based on your YP, f of t. And then you should decide, do you need to apply the modification rule? If you don't, right, then you proceed to the last step, which is to find whatever coefficients that's involved for YP, and in this case is C. And to get the solution for coefficients, you need to calculate its first order derivative, second order derivative, and then substitute into the original second order differential equation. Simplify, find a common term, okay, and then solve for the constants. Okay. All right, so let's take a look at any question for this example. So let's take a look at one more example, which is more of a, I wouldn't say it's a complicated, but it does involve a little more computation. Okay. And this question will be an example of the summation rule. Okay, let's say we have a second order differential given by this format. So you look at your right side, which is the so-called f of t. So maybe I should let's down step 1 first, and then we'll look at that. Step 1, homogeneous, characteristic equation for the homogeneous. So you lambda squared plus 2 lambda plus 5. Solve for lambda. This will give you a pair of a complex conjugate roots. Lambda 1 equal to -1, lambda 2 equal to lambda 1 plus J2, and it's -1 minus J2. So we usually call alpha is -1 and beta is 2. Okay. So you look at the handout or the lecture notes from the lecture on homogeneous second order differential equation. When the roots is a pair of complex conjugate roots, your solution is e to the power of alpha t, and then cosine beta t, and a here is constant. A cosine beta t and b sine beta t. Right, that's the solution when you have a pair of complex conjugate roots. E to the power of alpha t, a cosine beta, b sine beta. Okay. So those are the formulas you will be able to have for the final, but you have to be able to use it appropriately. Okay, so this is your step 1. Step 2. Step 2 is where we need to look at the YP, and this time you examine this f of t. It's pretty obvious f of t has 2 different functions. It's addition of 2 different functions. One is exponential function, and then plus a combination of sine cosine, right? So if I look at my table at here, so f of t basically is addition of this type of function and this type of function. So if I need to make a lucky guess, then f of t will be a choice of this plus a choice of that. Okay, yeah. So now what you typically can do is, okay, you can also, you should probably simplify this a little bit. So you can see YP, it consists of 2 particular solutions. Because this is YP1 and YP2. So YP1, right? So this is basically for that e to the power of 0.5 t. You can write down your YP1, right? And that's C e to the power of 0.5 t. That's based on the table. If your input is this, then your particular solution will be this. And then for the other one, that 40 cosine and then minus 190 sine. Okay, you can obtain a lucky guess yp2, right, based on the table, which is n cosine 10t plus m sine 10t. That's where your yp1, yp2 are from. Your overall is yp1 plus yp2, right? So this is your basically what we call the sum rule, right? The last rule over there, sum rule. Okay. And next step, yes. Over here for this, the positive sign. I mean, it doesn't really matter because you're going to solve for m, right? So m could be positive, could be negative. Yeah. So if you put a negative sign here, it shouldn't matter, but you probably want to start with a positive sign just for consistency. Yeah. All right. So once you get this step here, and then the next step, right, is to find this C and N and M values. So find the three unknown constants. Okay. So when you try to find the C and M, now this is where the approach can slightly differentiate a little bit. So some people will use YP, okay, together. So you basically, you put these two together, and then you take derivative YP prime, YP double prime, right? And you substitute the three back into this second order differential equation, and you try to solve in one shot, okay, which is doable. But oftentimes, what I would suggest is, right, you can separate this solving for C and M, okay, into two different steps. So first, try to solve for C only because that's C is associated with this exponential function. Okay? So you can do is you obtain YP prime, YP1 prime, and YP2 prime, double prime. So first get this expression. Of course, you already have YP1. Right? And then substitute back into Y double, your original function, Y double prime plus 2Y prime plus 5Y, and equal to e to the power 0.5t. So it's like you're basically solving a question, okay, separately. So you solve this one. And this one only involves that e to the power 0.5t. So your substitution yp prime, okay, back into here. So I'll leave that to you. I mean, this is a fairly straightforward derivative because it's exponential. Okay. So there really no trick at all. So you can get your C would be 0.16. Okay, if you do that. Sorry, I probably also had to mention before this step 3 at here, and don't forget to examine the modification rule. So you should examine your choice YP1 and choice YP2 and compare with your YH, your Y1 here, Y2 here, and see if they duplicate. In this case, obviously they don't duplicate, right? So this is e to the power negative t cosine, and this is cosine 2t, right? There's no duplication at all, so modification rule does not apply in this question. So far, so good, right? So this is your C value based on this equation here. And then next step is for the N and M. So you calculate YP2 prime and YP2 double prime. Now this one involves sine, cosine. So again, I would suggest that to be extra careful when you calculate the derivatives, because one difference of a sign will result in the mistake of the final result. So YP2 prime, okay, so this is your YP2. Its first order derivative give you negative 10a sine 10t plus 100m cosine 10t. Okay, that's your YP prime, YP2 prime. YP2 double prime is a calculation derivative based on YP2 prime. And you get negative 100 n cosine 10t. And then, I'm sorry, this is not 100, this is 10, right? Yeah. And then minus 100 m sine 10t. Okay. So that's YP2 prime and YP2 double prime. So now you substitute this YP, substitute into y double prime plus 2y prime plus 5y equal to 40 cosine 10t minus 190 sine 10t. So this time you're not dealing with the exponential e to the power 0.5t anymore. You're focusing on this cosine and sine here, right? Okay, so substitute. Here you substitute into this, and then that into here. So there's going to be a little bit long expression here. So, but before you do the substitution, right? Let's have a bigger picture. So here's your YP, and here is your YP prime. Here's YP2 double prime. So when you substitute everything into the left side, your idea is to group a similar term. So what I mean by similar term, basically you look at each one of the term, you have sine 10t, cosine 10t. So basically at the end, when you after substitution, you should group all of the terms associated with cosine 10t together, and then all of the term associated with the sine 10t together, right? So you have sine 10t, you also have a sine 10t over here. You have cosine 10t, cosine, and cosine, right? And also there's coefficient 2 and 5, so don't forget that. Right, so that's the ultimate purpose, right? After substitution, group all the term, and then the other side is 40 cosine 10t minus 190 sine 10t. So if you have this kind of bigger picture in your head, then it wouldn't be too messy, right? You wouldn't be too confused, after substitution. Okay. And after this step, you compare coefficients for the cosine 10t and compare coefficient of sine 10t with the other side. So the left side, the coefficient of cosine 10t should be the same as the 40 on the right side. The coefficient for sine 10t on the left side should be negative 190, right, on the right side. And that should give you two equations, which is 100n plus 20m plus 5n equal to 40, and negative 100m minus 20n plus 5n equal to negative 90. So two equations, two unknowns, okay, and you will be able to solve for the m and n. And of course, I didn't simplify. You certainly should simplify. So this is m here. Right, so there's negative 100m plus positive 5n, negative 100m plus positive 5m. Overall, you should end up with a value n equal to 0, m equal to 2. So that basically means your YP2 just 2 times sine 10t. Start is a gigantic equation, but end up is a very simple one. So your final solution, right, is YH. So your final solution is YH plus YP1 plus YP2. So put all of them together, and you get an overall solution, general solution for this second order differential equation. Right, so this example, if you reflect on it, you can see, you have a very complicated expression for f of t, but you can break it down into 2 different inputs, one exponential, one sinusoidal, and then you're essentially treating it like solving 2 different second order differential equations with 2 different inputs, right? I think the other cases will be more or less very simple case. So these 2 cases, right, the modification rule, which involve modification, and the summation rule, right, are probably the most complicated case to solve a non-homogeneous second order differential equation. Okay. Okay. Any questions? Yes. Yeah. YP2 double prime? Yes. Pardon me, last one. Would then that end up with what? Oh, no. We're not gonna, so look, YP1 is this, right? So it doesn't involve the YP2. And when you solve for YP1, you only keep this e to the power 0.5t. So your original function, you're not keeping this one here because you're only focusing for YP1, which is associated with this term. So you will not have any sine cosine show up when you substitute your YP1, YP1 prime, YP2 prime into the second order differential equation. What is what? What is YP? Okay, so let's see. So YP1 prime is 0.5c, this, right? Then YP1 double prime is 0.25 and c e to the power 0.5t. We're not dealing with YP2 here. Oh, sorry, this is a mistake. YP1 prime, YP1 double prime. Yeah. Pardon my handwriting, yes. Okay, good. Now, to go ahead, I remember there was a question asked by a previous student. Is that, so for example, right? So let's say AY plus BY prime plus CY equal to F of t, okay? So there is a question, basically, student said, what if F of t equal to, for example, 1 over t? Okay, yeah. Or maybe even more complicated, I don't know, let's say I'm just conjuring up some questions here. Let's say even 1 over ln t, okay, yeah. Or maybe even more complicated than, all different things, 1 t squared plus 1, okay, right? So all of these examples here for f of t, and if you look at them, they do not, right, fall into any one of the categories inside the table, right, that we listed at the beginning, right? They're not any one of these functions listed here. So that question was basically, what do I do, right? So obviously, you cannot use this method on determined coefficient anymore. So that we have to use a different approach. So this is what the next approach will be able to deal with this kind of situation, right? So if f of t is in is in the form of this kind of function, right? Then we will use the next approach called variation of parameters. So we'll use a variation of parameters approach. So that's what the remaining of this lecture and maybe also the next lecture is all going to be all about. So what is the variation of parameters? Okay. Yeah. So now let's bigger picture, right? Now we're still looking at so let's look at a second order differential equation given as y double prime ay prime plus by and f of t again, right? It doesn't take the format of the table anymore, okay? So to solve this type of equation in here, step one is very similar to that method of undetermined coefficients. So your step one is still to obtain the homogeneous general solution. So your YH. YH is C1, Y1 of t plus C2, Y2 of t. Okay, that's exactly the same approach. So the difference starts from step number 2. If it is a undetermined coefficients, or if f of t is exponential sinusoidal, right, you can use lucky guess approach. But this time you notice that you can't do that anymore. So what we do is, okay, we're going to derive a set of a formula. So what we're going to do is we'll start with by letting yp, okay, equal to m1 of t times y1 of t plus m2 of t times y2 of t. This is again, sort of like you might wonder why, right? But you'll see how it actually will work. Okay. So what y1 of t, y2 of t here, this y1 of t and y2 of t, right? They're the so-called basis solutions. They're from your homogeneous second order differential equation, characteristic equation. Right, so this is from the y1, y2. And then m1 of t, m2 of t are two functions that we need to find out. So this is actually where the name variation parameters come from. So you multiply y1 with m1, you multiply y2 with m2, in hoping that if you somehow change this function m1 and also m2, you're able to find a particular solution, yp, that satisfies this second order non-homogeneous equation. Right, so that's the logic thinking it here. Will that work? Right? We don't know, but of course it will work. Right? So that's called a variation. So this m1, m2, they're like the so-called parameters, right, of this y1, y2. I mean, you could multiply 2 or 3, but then it's called a constant parameter, right? But in this case, it's it's a time varying parameter, m1 and m2. So that's where the name of this variation of parameters come from. So you're varying this coefficient at y1 and coefficient for y2 in this expression in hoping that you can find an answer or solution for m1, m2 such that fyp is actually a solution to this one here. So that's the logic going on here. So of course, the question is, does it exist? If it exists, then what is M1 and what is M2? Okay, so let's find it out. Now, no matter what, right? So you're hoping that YP is a solution. So we need to calculate YP prime. We also need to calculate YP double prime. So if you substitute back into the second order differential equation, then this should be a solution, right? Satisfaction of this original. So let's calculate the first order derivative of this YP. Again, it's a little bit long expression because it involves product rules for each term. So I'm gonna get M1 prime T times Y1 of T plus M1 T Y1 prime, M2 prime, Y2 prime, Y2. And M2 Y2 prime. That's the result of the first derivative. Right. Product rule for each one of the term. Okay. So now we're gonna. Okay, this is where you might want to ask, well, why are you doing this? But we're gonna impose. Okay, impose means you're forcing a term to be zero. We're gonna force this M1 Y1 of T plus M2 Y2 of T. Okay, so we're gonna impose this term to be zero. So you're forcefully letting that two terms addition to be zero. You might wonder why, but you'll see actually by doing that, we're able to actually get a solution basically. Okay, so whatever the reasons behind this, it basically worked. It will work. Right. So if this term is being letting to zero, then the YP prime, right? It basically becomes M1 of T Y1 prime plus M2 of T Y2 prime. Okay. So now we proceed from here to calculate YP double prime. So your YP double prime will be based on this YP prime here. And then obviously you're gonna use product rule. Okay. Right. That's a product rule based on the YP prime. So now you have YP prime, and a YP double prime. So you sub the three terms. Okay, sub the three terms back into Y double prime plus AY prime plus BY and equal to F of T. Okay. When you after substitute back into this, right? We need to basically keep a sort of a clear head when you do simplification. Okay, so there are a lot of terms involved after you're substituting back into it. Okay, so your YP double prime is over here, and then your YP prime is over here, and then YP is over there, right? So once you substitute, you can group similar terms. Similar term basically means terms with common coefficients. Right? So the terms with common coefficient for M1 of T, and you end with Y1 double prime T plus AY1 T plus BY1 of T. And you also end up with M2 common term coefficients. And the last one, you have M1 of T. Let me just finish writing of this, and then we can call it a day. Now that's a gigantic expression, right? After you substitute everything back into the second order differential equation. However, you'll see a direct benefit. Okay. First of all, you look at the terms in the two brackets over here. And this is y1, this is y2. And they're what? They're actually 0. Why is that? Because y1, y2, if you recall, what are they? They are the solution, the basis solution for the homogeneous second order differential equation, right? So these are for the homogeneous one. So if you substitute y1 here, 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 should be 0. You substitute y2 here, here, it should also be 0. So that's why the two terms here, they're 0, they're gone. And they are actually direct results of this imposed condition here. If you don't impose that condition, then you won't be able to get the 2 0 terms. And that's why that imposed term actually worked. So you end up with just the last expression here. Okay. So now you have this expression, and you have this expression, you have this 1 and 2, and we'll be able to work from here based on these two equations. Okay, so we'll continue from here for the next lecture.